Morning, kids. We're going to talk about scatterplots today. And before we start, I wanted to give you a note that if you see a slide with this orange background, it's not going to be on the note sheet that we're going to ask you to fill out, but you probably should write it down anyway. So you're going to need a calculator, graphing calculator, TI 80 something would be preferred. And if you do have one of those, you should reset the memory so that you don't have any ghosts of problems past that are going to come back and bother with our settings. We're going to look at describing scatterplots in this video. So data collected from students in statistics classes included their height and weight. So here's a scatterplot of that. If we're asked to describe the association between the two variables, there's three things that we need to make sure that we include every single time we do that. We need to include the strength of the association. It's going to be either weak, moderate, or strong. You can add in some adjectives like fairly, moderate. You're going to describe the form, whether it's linear or if it's nonlinear. Now, you're going to have to harken back to some of your Algebra 2 experience for the nonlinear, but really just saying nonlinear is enough for AP. But you could think about what kind of nonlinear associations you might see there. And then lastly, direction. Is it positive or negative when we're talking about the slope of a line that might go through those points when we're talking about positive or negative? So as we look at this association that's here on the screen, as we go to the right, the trend seems to be going up, right? So this is a positive association. The taller you seem to be, there's more of an association with how much you're going to weigh. Survey was conducted in the United States and 10 countries of Western Europe to determine the percentage of teenagers who used marijuana and other drugs. Results are summarized in the following table. So this is percent who have used either marijuana or other drugs. You need to put that data in your calculator. So what we're going to do is we're going to come up with a scatter plot. But the way we're going to get this scatter plot is on your calculator, you're going to put the data in list 1 and list 2. Okay. Now, often, as we get further in this unit, we're not actually putting the data in the calculator. We'll have a computer output that gives us a summary statistics once the data has been crunched. But this is how we're going to go. So you can see I have the data in my calculator. Take a minute, pause the video if you need to put the data in your calculator. Then we're going to go to stat plot. So stat plot, we're going to turn it on. The first one is a scatter plot. List 1 is the X list, so it'd be marijuana on our X list. And list 2 is the Y list. That would be our other drug use by percent, right? These are percentages. Big one jumps out there. What the heck is happening in Scotland? So when we do this and we look at the graph, if I just hit graph, I may not see much. But I want to hit zoom and then go down to 9, which is the stat option, which will set the domain and range for us that makes it pretty nice. So here I can see this association that's also in my table here, okay? So I have this for us, but you need to be looking at yours. And if you hit on your calculator, if you're going through and trying to make this an AP quality graph, we're going to need to make sure we put labels. And then we need to put numbers on our axis. And a nice way to do that is to hit trace. And we can scroll through the list. And I might get the lowest X value, so I could put 5 here and know that this is 5. And my lowest Y value is 1. And then I can keep tracing through until I get to a point that's like maybe on the other extreme. And I know it's going to go up to 53, Scotland, and 31. And that'll give me just enough of a scale that I have a pretty good idea of what the numbers are looking like. So if we're going to do that for our numbers, and I just come in here and I say, okay, well, I want to put a scale. Here's 5. Here is 53. Here's 1, and roughly 31. And that's enough. That's an AP quality scale. You can certainly include more points, but this is enough for us. If we put the regression line in there, you can see the line going through the data. If we're going to do that on our calculator, when I go through and I hit to go to the scatter plot, Oh, actually, no, I have to go through this another way. So the way I'm going to get this line is to run some summary statistics. So to do that, I'm going to go to Stat, I'm going to go to Calculate, and I'm going to go to Linear Regression. Now, there's really important, kids. You see that there's two choices for linear regression here. And if you have an older calculator, you don't even see them both. You might have to scroll a bit. The cool kids are going to use choice 8, and I'm going to use choice 8 in this video for the reasons that we will become more apparent in the second semester. Just know that B is our sample slope in the second semester as well, so we want to be consistent with that. That's the only difference is here A is the slope, here B is the slope. We're going to use B as our slope. So I'm going to hit choice 8, and when I get down here to store regression equation, I can tell the calculator to put that in Y1. So if I hit alpha F4, there's a shortcut for that, or you can go to vars and go to yvars and go to function, which is a lot longer, right? And make sure it's Y1, however you do that. And then once we have that and we hit calculate, we're going to have the graph with the line in it. All right, so some things to talk about. We'll come back to the rest of those summary statistics and settings on our calculator in a moment. But when we have a correlation, when we have an association between two variables, it doesn't matter what units we use. Because if we scale them, we're going to scale all the points the same way. We can have height in inches, height in centimeters, weight in pounds, weight in kilograms. It's going to look like the same scatter plot, especially if we step back and look at it and aren't paying attention, right? These are the same association between the different observations. It does not depend on units. Shifting and scaling does not affect correlation. So that's one thing that you may want to keep in mind. Correlation treats X and Y symmetrically. So if we look at horsepower and gas mileage, the more horsepower you have, probably the bigger engine you have in your car. So your gas mileage is going to decrease, right? As horsepower increases, gas mileage decreases. If we change that and put gas mileage on the x-axis, as gas mileage increases, horsepower decreases, because these are the smaller cars with like a 3-cylinder engine. Still had the same association, the same correlation here, which we'll talk about in a moment. If we swap X and Y, the correlation does not change. All right, so what is correlation? Well, this is the correlation coefficient is R, and there's a little summary for R in the back middle of our handout that you're going to want to be able to reference. So if you're playing along at home and you have that summary talking about this piece of your worksheet on the back, there's a big summary thing. We're talking about correlation. Everything that we have here helps you name it, right? So if we have an R that is around negative 0.95, negative, if you look at the negative signs, all this is telling us is the direction. Negative, as we go to the right, we're going down. But the magnitude of the value is telling us the strength. So if I have an R value between negative or between 0.8 and 1, negative positive doesn't matter because that is just, so we're talking about the magnitude, then we would say that's a strong association. Now you have something like 0.95, you can say very strong, add that adjective. We can have a moderate association between roughly 0.5 and 0.8. And we have a weak association after, if it's lower than 0.5. And you can see here, our weak association, this, we can't really tell if this is going to be aligned this way, this way, this way, who knows, right? But here we have still, you can see it's trending negative, but their points aren't very close to the line. So when we talk about this, this is kind of a measurement of how close are the points associated with the line that we're using to model it. All right, this is the bottom of the first page of your worksheet. So this is that first one on the first page at the bottom. If we're going to look at this association, first of all, we see it's positive, right? So we're going to have a positive R value. How close do you think those are to the line? So we're going to think of it somewhere between 0 and 1 because it's got to be positive, right? So this is these points are fairly close to a line that we would have going through here. It's just somewhere between 0.8 and 0.9. Take another one. This is the second one on our association at the bottom. These points don't look like they're associated at all. This would be fairly close to 0. Oh, I don't know what's happening here. Okay, so fairly close to 0. Here we have a negative association, right? As we go to the right, the points trend down. And they're not all that close together, right? So if we're going to talk about this R value, we know it's negative, but also probably 0.6 or 0.7, it's moderate. And then lastly, we have this U-shaped graph, or I guess it's not lastly, we have this U-shaped graph. If we had something like this, a linear model is not going to fit this at all, okay? So we're talking about a linear relationship. And if we don't see a linear relationship, then we're going to say 0 anyway, okay? If we had really had to do something with this, we could like make it into a piecewise function and talk about up to this x, it's negative, and up to this x. But in general, as a whole, for AP statistics, which is, we would see something like this and say, nope, we're going to punt. The last one we have, these points are really strongly associated, right? They almost look linear anyway, and it's negative, so this is going to be pretty close to -1. Okay, so we're going to interpret the correlation coefficient of our association. So we're going back to our calculator here, and we're looking at how close do we think these points are to this line. And if we go back and we run the summary statistics, we're going to calculate, and we're going to use choice 8 because we're cool kids. And I go down here. I already stored the regression equation, so I'm not going to store it again. I hit calculate. I'm looking, usually we'll have an R value here. If you reset the memory on your calculator, which we tried to prompt all of you to do, the default, for some engineering reason that I don't understand, is to turn that off. So you're going to have to go to mode, and we're going to find the stat diagnostics, and we're going to turn those on. Okay, so once I have my diagnostics on, when I run the regression, now it gives me R and R squared. Okay, so the note to make to yourself, make sure your stat diagnostics are on if you're using raw data, which a lot of times we won't in this class. But if you're going to take what we learned in this class and apply it to other places, here you go. So here's our R value. Okay, so you can see in our video, 0.9341. So if we see a R value like that, and we look at the scatter plot and we think, oh, that's a linear relationship, then we would say there is a strong positive linear relationship between the percent of teens who use marijuana and the percent who have used other drugs. So we looked at the scatter plot, right? This is well, many slides ago, but when we look at the scatter plot, we can decide if it's linear or not. So if I'm looking here, I don't see a nonlinear relationship. It looks fairly linear to me. I don't see a curve in the data. So when we're talking about strength, form, and direction, we have strength. We would probably put in linear here somewhere. Only if we know it is, okay? So if we know it's linear, then we can put that in there, but this is an important thing. Don't just look at the R value to decide, because we can come up with examples that have an R value of 0.99 but are exponential, okay? All right. Correlation is very sensitive to outliers. If we have an outlier here, shoe size of 30, and we're looking at IQ, you might look at this association and say, oh, there's no relationship. But as soon as you put a point there, the computer program tries to put a line through there, or really any math model that we use to come up with a least squares regression equation. It's going to try to include this point and put a line through there. This is our outlier. This is actually a very high leverage point. So If we get rid of our outlier, then it looks like we don't have an association at all, which is what we expect. This looks pretty random to me. There isn't really an association between your shoe size and your IQ. We look at the coefficient of determination, and we're going to change this from a decimal into a percent. It's one of the few times we do this in this class. Most everything we report as a decimal, and we keep it as a decimal even when it's asking what's the percent of anything. But when we're talking about coefficient of determination, we're going to change this from 0.8725, and we're going to talk about it as about 87.3%. Okay, so we're changing this to a decimal or a percentage. This is down at the bottom of our page right above those scatter plots that we were choosing the strength for. About 87.3% of the variability in whatever our y value is, it doesn't matter, this is the kind of like the structure of the sentence, can be explained by the linear model for x and y. And then we want context, okay? So we're thinking about this. We have teens who tried marijuana, and then we see if there's an association between teens who are using other drugs. And so we want to talk about the 87.3% of the variability in teens who are trying other drugs can be explained by the linear model for percent of teens who use marijuana and the percent of teens who have tried other drugs. Okay, so there's our sentence. This goes in the very bottom, but the structure, this framework, is really how you want to learn it and memorize it. And we just slap in the context. Okay, so there's some other stuff here. If we're looking at this as a linear equation, which it is, then we have the slope is the coefficient in front of x, and this makes this the y-intercept. So when in part C it says, write the least squares regression equation, we have the y-intercept, we have the slope, we already talked about coefficient. We're going to write in context, okay? You have a choice. You can write y hat equals negative 3.068 plus 0.615x, but then you have to define x and y. That's a lot of work if we're going to write it anyway. So this essentially becomes this idea of y hat equals a plus bx. That's supposed to be a plus sign. This is our predicted y, okay? Predicted. That's telling us, hey, this is the line that's going through those points. It may not even hit a point. It's just where we're guessing. It's kind of like the average, right? We're in the middle of those points, and it's not a guarantee. So our least squares regression equation, we're going to interpret the slope for part D. Slope is 0.615. Now remember your slope, right? We have rise over run when we're talking about slope. And if we have a decimal, we're just going to say, well, this has a run of 1. Okay? We can make anything into a fraction by just putting it over 1. So we're going to take that 1 and we're going to say for every 1% increase in teen marijuana use, this is X. The model predicts, our model, the model we just had, our y hat model, predicts an increase of, this is our slope, 0.615 in, here's our y value, right? The percent of teens who use other drugs. Okay, so there's X, here's Y. So the y-intercept, remember when we're on the axis, our y-intercept, wherever we are, is when x equals 0. So when percent of marijuana, this is our x, when x equals 0, y, the percent of other drugs, is predicted to be negative 3.068%. Okay, now obviously that's extrapolation because we didn't have any x values that were close or were 0. The smallest one we had was 5. So Finland, but we had to extrapolate a little bit, which puts the y value, the y-intercept below the axis. So when you're thinking about these sentences, interpret the slope Okay. Make it rise over run. Interpret the intercept. Okay. Make x equals 0. Careful with wording. When percent marijuana is 0, percent other drugs will be the predicted value. You got to be careful about will be. We're predicting it to be close to a value, but we don't know that it's going to be that value because the points don't line exactly on the line. We don't have an R value of 1. If it was R value 1, it'd be perfectly on that line. Since our line misses many of the points, the residuals are a measure of this miss. Residual equals y minus y hat. That's our observed minus predicted. So here's our fictitious scatter plot. And we have points that are closer, maybe not so close to the line. The points are observed. These are our actual. Okay? So here's an actual point. This is the predicted value that we would have for our actual point. So our residual is the vertical distance from that predicted value to the point. If we're doing actual minus predicted, this is a bigger y value, right, than what we predicted. So this would have a positive residual. And here we overestimated, right? Our line was higher than the actual point. So our actual would be lower, and we subtract the predicted, and this is going to have a negative residual. If we took all these distances and graphed them, we would have some that were above 0, some that were below 0. The line essentially becomes 0. So when we do a residual plot, what we're doing is we're taking that line and kind of turning it so it's flat. And this is the distance from the line. If it's right on the line, it's 0 residual, right? So we have positive residuals. These points were all above the line. We have negative residuals. These points were all below the line. You can see how these points associate with our residual. The scale gets a little bit different in the y values. Okay, so we want to find the residual for Scotland. Scotland had that 53% of teens were using marijuana and 31% of teens tried other drugs. And we really don't know, kids, if these 53% also were part of this 31%. So we got to be careful about cause and effect here, but this is the data that we have, right? So this is the actual y. To find the residual, we're going to do the actual y minus the predicted y. To do the predicted y, we need to come in here and plug 53 into our least squares regression equation. If we do that on the calculator, if I get back to the home screen, I can do that by going to alpha F4. This brings up our bars here, and we're going to just say, okay, this is f of 53. And when I do that, it gives me back my 29.527. So I'm going to use that predicted y. So I'm going to use that to find the residual. So I'm going to do 31, my actual, minus the predicted. I get 1.473. Now, when we look at the graph, we can see that that point is above the line there, right? We're a little bit above 1.473% more than what we predicted. So the percent of teens who used other drugs in Scotland is 1.473% more than, we're interpreting the residual here, what the model predicts based on teen marijuana use, based on the X value. There is a high correlation between the gender of American workers and their income. What's wrong with this statement? High correlation between gender of American workers and their income. When we use the word correlation, what we really are talking about are two numerical sets of data that we're associating on a scatter plot. Gender is not a numerical set of data. It's categorical. So we could do one of those segmented bar graphs, and we can look at the categories of those things, but we can't look at a scatter plot. If describing the relationship between categorical variables, use the word association and not correlation. And that's it. That's it for our notes, kids. Please go back and submit your note sheet.